our plan is, and this is going to take several weeks actually, um, to consider notions of computing real numbers, single numbers, three notions that all are reasonable and that turn out to be equivalent non-trivially. And this serves as strong evidence that these notions are indeed reasonable notions. And then we consider examples of computable real numbers, and we consider counterexamples of uncomputable real numbers. Then we move on to kind of like higher types. First, we consider sequences of real numbers. And there we study the computability and uncomputability of the test for equality, thus providing a rigorous justification and foundation of this numerical folklore, don't test for equality. Then we prove that every computable sequence misses a computable real number, which is kind of interesting because, as you know, there are precisely countably many algorithms and therefore also countably many real numbers. So it could be, from a simple counting argument, cardinality argument, it could be possible to have a sequence that enumerates all computable real numbers, and indeed this is possible, but not necessarily not a computable sequence. This will be turn out to be a very interesting variant of a diagonalization argument that we already know from the proof of undecidability of the halting problem. Then we move on to the next higher type, real functions. We consider notions again of what it means to compute a real function. We show that this notion is reasonable by exhibiting its nice closure properties, closure under composition, closure under restriction, and when plugging in a computable sequence into a real function, turns out to give again a computable sequence. Then we show that every computable real function must necessarily be continuous, which is sometimes considered quite surprising, a restriction, but this is just a consequence of the definition, and we will later consider variations that suggest that allow to avoid this serious topological restriction. And then we consider a computable version to the Weierstrass approximation theorem, classically allowing or asserting that a continuous function in a compact domain can be uniformly approximated by polynomials. And there's equivalence to this first notion and computable Weierstrass notion. This will lead us to closely look at compactness in real computation, which is a new perspective. It turns out that this has already been present in discrete computation, but it has been hidden there because in discrete case, a space is compact if and only if it is finite. And so in the discrete case, there are many cases where there's a hypothesis that something is finite, or there's an assertion that something is finite. And indeed, this turns out to generalize to the continuous realm where finiteness now becomes compactness. Then we consider advanced aspects of computing real functions. Namely, we show that root finding is uncomputable in a very strong sense, and so is argmin. And we demonstrate that taking derivatives even of continuously differentiable functions is in general uncomputable an operation. We recall the proof that the wave equation can lead to uncomputability, and also that all ordinary differential equations can have uncomputable solutions only. And then we proceed, as already mentioned, to these extensions, ways of avoiding the restriction that any computable function must be continuous. And there are two kind of, if you like, workarounds. One is to consider multi-functions, also called non-extensional functions. And the other is by adding discrete enrichment to the argument of a function. And so we're going to define what it means to be a multifunction, what it means to compute a multifunction. We're going to recall some generalization of our classical notions, in particular the notion of a restriction. We're going to look at the fundamental theorem of algebra that you all know from complex analysis from the computable perspective. We're going to study the fuzzy sign test as a way to avoid the uncomputability of the classical sign test and computability of the Archimedean property of the real numbers, which again requires multivaluedness. And then we consider two classical problems on classical calculus, namely the standard operations in linear algebra and analytic functions and analytic continuation, and prove them to be naively uncomputable, and then how to apply this to extensions, to multifunctions and enrichment to make both of them actually computable. And finally, in this long chapter 2, we will close with discussing what it means to compute a real operator. That's the highest type we're going to consider in this lecture, operator or functionals. And to this end, in order to input functions to the computer, to the computation, we must discuss how to encode continuous function as arguments and how to encode compact subsets as arguments. So this is going to be a long chapter, and but we're going to, it is carefully subdivided into 6 subsections, and similarly, the lecture will proceed very carefully to climb up to these more and more difficult topics, climbing up more and more up the type hierarchy. Okay, so let's start by recalling these announced 3 notions of what could it reasonably mean for a real number to be computable. And the first natural notion is to define it in terms of what notions we already know, namely what the decidability in the discrete setting. And this notion can be used to carry over to a single real number, right? So in the discrete setting, with decision problem is in general an infinite set of natural numbers. And here we have only one single real number, but they can be put in a correspondence via the binary expansion, right? So we consider the binary expansion of this real number. Let's say it's a real number between 0 and 1 to make things simple. And then there's this sequence of binary coefficients of zeros and ones. And we consider the decision problem given an index, maybe encoded in natural numbers or whatever, to tell me whether the binary coefficient with this index is 0 or 1, or put differently, answer yes if it's 1, answer no if it is 0. That's a classical decision problem, and this is actually basically the notion that Alan Turing himself used when studying computability of real numbers in his famous paper from 1936, 1937, where he also introduced what we nowadays call the Turing machine. So that's one reasonable notion, but there are other notions which are arguably closer to numerical computation, and the notion, second notion we're considering here is approximating the real number by dyadic rational, which is kind of a generalization of floating point numbers. Dyadic rational is a rational number, a fraction, where the denominator is a power of 2, an integer power of 2. So that imposes a considerable restriction on the denominators. And right, so every floating point number has a certain mantissa length, and so this can be regarded, this numerator can be regarded as the mantissa, and this is kind of the exponent. And the requirement is that this sequence of floating point numbers must approximate the real numbers with this error bound, fast converging error bounds 2 to the minus n, not 1 over n, for reasons that I will explain later when we talk about more advanced aspects and in particular about complexity theory. Okay, so this is a second reasonable notion coming formalizing from multi-precision computation in numerics, and a third notion originates in logic or constructive mathematics, namely approximating the real number by general rational sequences. So numerators and denominators can be arbitrary integers, and there's a error bound which must also be some computable sequence of denominators, right? And here we have this 1 over something as opposed to 2 to the minus something. And the only requirement is that these approximations satisfy the error bound, and that this error bound eventually converges to 0, but there's no requirement about how fast these error bounds must converge to 0, whereas here it must converge to 0 very quickly, and the rational approximations must have a certain form with a denominator. So these are all reasonable notions, and fortunately we're not forced to choose between them, because fortunately one can prove, we're going to prove soon, that they're all equivalent. And as I mentioned, or keep mentioning generally, meta-theoretically speaking, meta-mathematically, several reasonable but distinct notions turn out to be actually equivalent. That usually is strong evidence that these notions are reasonable and worthwhile further investigation, like developing a theory upon them, which is exactly what has been pursued since seminal and initiating work of Turing. There's also a fourth notion that sometimes underlies analysis of numerical algorithms, maybe computing a sequence of rational approximations like this that converge to the real numbers, but there's no error bound involved. So here we have error bounds and rate of convergence. Here we only have error bounds with arbitrary rate of convergence, and here it's just convergence without rate and without error bounds. And so that's kind of like eventually convergence. And this has been shown by Ernst Becker in 1949 to be a strictly weaker notion than the other three, which are equivalent, significantly weaker in the sense that converting this to any of the other three in general is equivalent to granting oracle access to the halting problem. You recall from our first section on computability theory that right, we have this Oracle Turing machine. Well, in our setting, we use Oracle while programs, and having Oracle access to the halting problem, that's something rather powerful. For instance, we could prove this Schoenfeld limit lemma. And here we're going to prove a counterpart, a real version of the Schoenfeld limit lemma. Okay, here's for your convenience a reminder of what it is, what the halting problem is. Okay, so that's a statement, and in the sequel of this lecture we will thus be able to freely move and switch between any of the three notions, but first we need to prove them equivalent. Okay, and in order to prove them equivalent, so we're going to prove A equivalent to B and B equivalent to C. That's the strategy. And from A follows B, that's pretty immediate. Namely, consider AN to be basically the sum of the first scaled binary coefficients, right? So here, if we take this infinite series and cut it off at some point m, then the rest of the series has value bounded by 2 to the minus n, right? So that's a geometric series, the tail of that series. And the initial segment, therefore, in turn constitutes an approximation to the real number r up to error 2 to the minus n if we only consider the first n terms of this infinite series. And since the binary expansion is supposed to be decidable, that means we can compute the the numerator of this dyadic approximation by taking the first n elements. This is where the decidability hypothesis really enters. So that's one direction, A implies B. And for the converse direction, that's actually more subtle because in general there can be carries, right? So we have an approximation of something up to error 2 to the minus, let's say 2 to the minus 10. But the approximation is like 1 over 2 to the minus n, 2 to the minus 10, 1 over 2 to the 10. Then the actual value could be 0, or it could be 2 to the minus 10, right? Both is still within the realm of approximating up to error 2 to the minus 10. And in particular, we cannot really know what is that digit, right? If the last digit could be 0, last digit could be 1, or the last two digits could be 1, 0 if it's a 2. And it's more generally, we cannot even determine an approximation. We cannot even determine the first bit of the binary expansion. Let me illustrate that. Let's consider the one number 0.5, right? 1 over 2. That can be approximated by 0.100000, right? But it can also be approximated by 0.011111, right? And so all of these approximations do not allow information theoretically to conclude anything about even the first bit of the binary expansion. So that means that a naive proof that item B implies A is bound to fail. We need a more elaborate argument. And to this end, here are two lemmas that are useful. The first lemma says, what is crucial about item B, dyadic approximation up to error 2 to the minus n, is actually the error 2 to the minus n. Because the lemma says if we approximate the real number x by some other real or other number y up to error 2 to the minus n plus 1, so one half better than required here, then by rounding that number, well, to the closest dyadic rational with the denominator 2 to the n. This is what that means. This brackets mean round to nearest. That rounding occurs at most an error of 1 over 2, right? Integer rounding. And after scaling it back with 2 to the n, that means that incurs an error of 2 to the minus n minus 1, right? And together with this error, by triangle inequality, it means that this number is now indeed a dyadic rational with denominator 2 to the 2 to the n. And this approximates the original real number x up to required error. So the message here is the crucial part is to get any arbitrarily good approximation, but not necessarily by dyadic rationals, because we can always easily convert any other form of approximations like rational numbers to dyadic rational approximation. And that will turn out to be useful when proving the equivalence between B and C. But for the equivalence between B and A, or rather for the implication from B to A, we're going to prove this by considering two cases. The first case is when the real number is actually itself is a dyadic rational, so a special rational number of the form numerator divided by 2 to the n for some fixed numerator, integer numerator. And this is a special big case because in this case, this dyadic rational, these special real numbers have actually two binary expansions. If you look closely, there's a subtle formulation here, namely the condition A says that R has a decidable binary expansion because it may have several ones. And the important question is, which one do we want to be decidable? Unfortunately, the answer is it doesn't matter because the only numbers that have two binary expansions are exactly the dyadic rationals. And to illustrate that, recall again the real number 0.5, 1 over 2. This has the two binary expansions 0.10000 and so on. And it has the other binary expansion 0.01111111, right? And both are, of course, decidable. They're, in a sense, trivial in that there's a finite initial segment, 0.1 in the first case, 0.0 in the second case, followed by infinitely many repetitions of the same digits. In the first case, zeros, and in the second case, ones. So from the perspective of decidability, both are easy to decide because the only thing to look at is the initial segment, and all subsequent digits, the answer is just the constant answer, 0 in the first case, ones in the second case. And all other real numbers have a unique binary expansion. All rational numbers that are not dyadic rationals, all irrational numbers, and all transcendental numbers have a unique binary expansion. So from the perspective of computability, we can almost like speak of the binary expansion. And when it's not unique, both are decidable and both refer to a dyadic rational number. So that the dyadic rationals are have immediately decidable binary expansion. So we're now proving that B implies A. It suffices, it remains for us to consider the case where the real number R is not a dyadic rational, where the real number R has a unique binary expansion. And we're actually going to construct an algorithm that converts approximations into the sense of B into a binary expansion in the sense of A, provided that the real number under consideration is not a dyadic rational. So this is basically the proof from B to A considers two cases separately, and the question which case is currently applicable, that's something that we defer to other discussion. This is a kind of existence proof that there exists a while program that decides the binary expansion. It does not touch the question how to arrive at that while program. I like to compare that to the decision problem of whether there exists a God or not. This is a decidable decision problem, right? Namely, to consider two algorithms, one that says yes, and another one that says no. And one of the two algorithms gives the correct answer. We may not know which one, but certainly the problem is decidable. And similarly here, we're going to show that there exists an algorithm which decides the binary expansion of a real number in case the real number is not a dyadic rational, and there trivially is a possibly very different algorithm that decides the binary expansion of the real number, provided that the real number is a dyadic rational. Okay, so how does the algorithm proceed that converts approximations to a non-dyadic rational number R into its binary expansion? The algorithm repeatedly applies the following lemma. So let me introduce and explain and prove to you the lemma. The lemma says, if we have a real number and we have this sequence of numerators of dyadic approximations up to error 2 to the minus n of that real number, then the real number is negative if and only if one of the integer numerators of these approximations is strictly less than 1. And similarly, the real number is strictly positive if and only if at least one of the numerators is strictly greater than 1. So let's prove the second equivalence, and the first one proceeds similarly. So first thing, if some numerator is strictly greater than 1, then by triangle inequality, right, this approximation is strictly greater than 2 to the minus n, but it is an approximation to the real number up to error less or equal to 2 to the minus n. Therefore, the real number cannot be 0, nor can it be negative. It must be strictly positive. It's one direction of the equivalence. And for the converse direction, if the real number is greater than 0, then it is greater than 2 to the minus, strictly greater than 2 to the minus n for some n, and therefore the approximation up to error 2 to the minus n must also be strictly greater than 2 to the minus n, and that's exactly what is written here. Okay, so this is what in constructive mathematics is sometimes considered as a certificate of being positive. Okay, and similarly, this is a certificate of being negative, and observe that the lemma does not say anything about a certificate of being equal to 0, the third case, because there is no such certificate basically. So this is going to be the difficult case when the real number is actually 0, or more generally, when the real number is a dyadic rational, which I'm now going to explain. So consider these approximations, and using this method, we can have a while program search, right? Search for a certificate for this real number to be, let's say, greater than 1 over 2, right? By adding 1 over 2, we can similarly search for a certificate, or we can formulate a certificate for being strictly greater than 1 over 2. And being strictly greater than 1 over 2 means that the first binary digit after the binary point must be digit 1. And so that this basically amounts to searching, have a while program search for a certificate for the first binary digit to be 1. And similarly, by looking for a certificate that the real number is strictly less than 1 over 2, one can look for a certificate and thus obtain a certificate that the first binary digit is actually equal to 0, right? So real number strictly less than 1 over 2 means the first binary digit must be a 0. And the third case, there the real number is equal to 1 over 2. This is the case that is not covered by this lemma, but fortunately this is the case we have already treated separately. Namely, this is the case where the real number is a dyadic rational, right? So this cannot occur tertium non datur. We by simultaneously running both searches, right? This is like this dovetailing technique that we talked about when we proved that the problem is decidable if and only if it is semi-decidable, and also its complement is semi-decidable. The same dovetailing technique, the same parallel search, which of the two cases is present, that succeeds here, because the third case we have excluded mathematically. And this leads the first binary digit after the point. And similarly, I leave it to you to adjust these, the lemma, to adjust the certificates. One can search for a certificate for the second binary digit to be 1 or 0, depending on what the value of the first certificate was. If the first digit is 1, then we may, for instance, subtract 1 over 2 to reduce to the question whether the real number is greater than 1 over 4, strictly greater, or strictly smaller than 1 over 4 to determine the value of the next digit, and so on. Okay, so this is a argument, and this is the algorithm that converts from B to A. And let me again emphasize two important aspects of that algorithm. First, that algorithm really relies on the real number under consideration to be not a dyadic rational. Dyadic rationals are treated entirely separately using an entirely different kind of algorithm and approach. And also there's no running time bound feasible for this conversion, because there's no bound on how long or how large the certificate could be, at which point this distinction occurs. The closer r is to 0, the larger n may be here or here. And so there's no uniform running time bound. The running time bound will depend on how close r is to 0. Okay, so this concludes our proof that A and B are equivalent. Converting from B to C is again easy, right? So we just use the same sequence A, and for B we use the sequence 2 to the m, right? This is 2 to the m, and for C we use the sequence also 2 to the m, right? You see this, then Cm is 2 to the m, then this is exactly this error bound. And again, the interesting part is the converse implication that C implies B. And to this end, observe that since this sequence 1 over Cm tends to 0, there must exist a subsequence of this sequence which converges to 0 exponentially fast, namely a subsequence where Cm is greater or equal to 2 to the m, right? And it remains for us to find such a subsequence, because then we have rational approximations up to the real number, and using the low lemma here, these rational approximations can then be converted into dyadic rational approximations. And so it remains to algorithmically find this subsequence, and this can be done again by unbounded search, right? We can search for such an m where Cm is greater or equal to 2 to the n, and the hypothesis, the specification guarantees that such an m exists and will eventually be found. But again, we cannot impose any runtime bound on how long, on how large m could be for this to happen. So this is really all about computability, theoretical equivalence. When we much later talk about complexity, these three notions actually will turn out to be very different. The equivalence between A and B complexity theoretically actually has been shown related to the P versus NP problem. So if you want to show A and B complexity theoretically equivalent, then know what you're up for. Okay, so this concludes our discussion of the three notions of computability for single real numbers. And fortunately, all three notions have now been established to be equivalent, and we may will thus freely switch back and forth between them when we want to conclude or use the hypothesis of a real number to be computable. Okay, and about the fourth condition, I'm going to return to that in a moment. And but before, let's talk about some examples of computable real numbers, and then finally the example, Specker's example of an uncomputable real number. Namely, he constructed maybe arguably the first uncomputable such number. So already made the first observation that every dyadic rational has two binary expansions, both of which are decidable, actually polynomial time decidable, the constant time decidable, because there's only finite initial segment, and from there on we can just give the constant answer. So dyadic rationals are trivial from a computability and complexity point of view. Rational numbers also are trivial. Every rational number has a periodic binary expansion, if you remember from your number theory classes. So again, by hard coding the period part and the initial part, which are finite, one can easily obtain an algorithm that decides the binary expansion of this rational number. Closure properties. Yes, so if A and B are computable real numbers in any of the three senses we've just discussed, then also their sum, their difference, their product, and their multiplicative inverse, provided that the number is non-zero, are again computable. And this can be maybe most conveniently proven using the, for instance, the dyadic rational approximations, or using the rational approximations, where we just need to make sure, since here we have the sum, the proof is basically very similar to the classical calculus proof, that if you have two sequences that converge to A and B respectively, then the sum sequence converges to A plus B. And you recall the similar proof, if you two sequences AN and BN converge to A and B, then the product sequence AN times BN converges to the product A times B. And similarly here, the difference to the classical calculus proof is here we need to take into account the error bounds, explicit error bounds, or explicit rate of convergence, which the classical proofs actually provide if you look at them more carefully. So let me skip the proof here and leave it to you as an instructive homework assignment, how classical proof in calculus carried over to computability theoretical proofs here. The next interesting item is about polynomial. Any polynomial in one variable with real coefficients. So it has finitely many coefficients. Maybe, let's say, if the polynomial has degree d, then it has d plus 1 coefficients, right? And the claim says if these coefficients are computable, and if we have take a computable real number argument and plug it into this polynomial, then the value of that polynomial is again a computable real number. So whenever x is a computable real number and the polynomial coefficients are computable, then the value p of x is again computable. That is kind of easy to see. That's basically just an inductive application of these two properties, because polynomial is comprised of these arithmetic operations, right? Addition and multiplication. And we have all numbers are computable, the argument and the coefficients, and also the powers, right? In the polynomial, there are some powers, but by induction, also the powers are computable. So that's one easy direction, but maybe the interesting part is that there's also opposite direction, a converse, namely if the polynomial has a property that its value is computable for all computable arguments, then necessarily its coefficients must be computable real numbers. And so that this is real and equivalence is the characterization. And the proof of this converse property can be follows, for instance, from considering the Vandermonde matrix. Maybe if you recall, evaluating a polynomial that's basically multiplying its coefficient vector inner product with a vector consisting of the powers of x, x to the 0, x to 1, 1, and so on, up to x to the d, where d denotes the degree of the polynomial. So that evaluation basically amounts to multiplying the coefficient vector to the vector of powers of x, finite many. And if we consider another computable real number, that gives rise to another vector of powers of x. And if we put all these vectors of powers of different computable real numbers x into a matrix, that constitutes a Vandermonde matrix. And Vandermonde matrices with different generator entries x are known to be invertible, right? So there's the famous Vandermonde determinant, and this determinant can be used to express also the inverse of the Vandermonde matrix, right? Using, for instance, Cramer's rule, one can express the inverse of any matrix as fractions of determinants, and determinants are all polynomial functions, um, so that the determinant of any matrix with computable entries is again computable, and fractions are also computable. So according to Cramer's rule, we observe that the inverse of a matrix with computable entries again consists only of computable entries. And in this case, the matrix under consideration is the Vandermonde matrix, right? With computable entries, namely with entries, the powers of several computable real numbers x. We just need d plus 1 distinct, pairwise distinct computable real numbers x. They can actually be the first n natural numbers, for instance. They are all computable, right? And we put them into a Vandermonde matrix. This is going to be a matrix that describes the evaluation at these computable real arguments. And since it's computably inverse of Vandermonde matrix, we can apply it. We can multiply the inverse Vandermonde matrix to the vector of values of this polynomial on the d plus 1 different arguments, computable arguments x. And this will recover the coefficient vector, right? So Vandermonde matrix times polynomial coefficient vector gives the value vector, and conversely, inverse Vandermonde matrix times the value vector recovers the coefficient vector. And this is again also basic linear algebra using arithmetic operations and therefore computable. So this concludes our argument, the proof of the equivalence in item D between polynomial coefficients being computable and the values being computable for any or just any d plus 1 computable arguments. Right, talking more about positive examples of computability, every algebraic number is computable. Why is that so? Well, every algebraic number is by definition the root of an integer polynomial, right? A simple root of a primitive integer polynomial. And this simple root can, for instance, be computed using binary search or using Newton's method if you want it more efficiently, but at this stage we don't. So the baseline is that the root, every isolated simple root of a polynomial is, with integer coefficients, is a computable real number. And that's what an algebraic number is, right? But also transcendental numbers are computable, at least some of them. For instance, pi is computable. Take your favorite algorithm for computing pi, like Bailey, Borra, Bluffy formula or whatever. This is an algorithm that computes pi, approximates pi up to any desirable error. And also E, the constant 2.7 and so on. That's also computable. For instance, yeah, we'll return to that question when we talk about computable functions. But well, not every transcendental real number is computable. Not every transcendental real number can be computable for cardinality reasons, right? As you know from transcendental number theory, there are uncountably many transcendental numbers. Well, because there are uncountably many real numbers, but only countably many algebraic numbers. So the rest must remain uncountable. But there are only countably many algorithms, right? And countably many algorithms are already used to compute all algebraic numbers, right? Because every algebraic number is computable. So again, only countably many transcendental real numbers can be computable. And most of the real numbers, most of the transcendental real numbers are not, such as the number that we're going to see in the next example, maybe the example of an uncomputable real number. But first, final round of positive observations, namely closure properties under certain functions, transcendental functions like the exponential function or the trigonometric sine function or the decimal or natural logarithm function. they all map computable real arguments to computable real numbers. And one proof for this can, for instance, be by considering the power series expansion of this, and we'll give that proof actually later when we talk about computable analytic functions. So allow me to defer that proof until later. But now, as I already announced, first count example, negative example, namely an uncomputable real number. Well, if you recall from this slide here, it's easy to come up with an uncomputable real number, namely based on item A. If we just take an undecidable problem and use that as binary expansion of a real number, right? So for instance, we can take the halting problem, which in our conception is a subset of the natural numbers, and taking that as binary expansion of a real number, putting a binary digit 1 at every index, at every natural number that corresponds to a terminating while program, and putting a binary digit 0 at any natural number n that corresponds to a non-terminating while program. This is pretty artificial, to be honest, I admit, but it does give rise to a problem which by construction has an undecidable binary expansion. And now things start to become maybe some interesting, because as you recall, all three properties we have shown them equivalent. So that means the real number whose binary expansion is the halting problem cannot be approximated in this sense, nor can it be approximated in this sense, and it cannot be algebraic, right? Because any algebraic number is computable, but the way we've constructed it by encoding the halting problem, it's not computable, so it must be transcendental numbers. So that computability theory gives rise to many transcendental numbers that mathematicians have not been aware of as a subclass. And here's now finally Specker's result, the famous Specker sequence. Namely, this is a sequence which is computable in the sense that I will formalize in the next slide when we talk about computable sequences. Actually, it's a strictly increasing, strictly non-decreasing and bounded sequence. So, and you know, every non-decreasing sequence, bounded real sequence, must have a supremum, which coincides with its limit. And so does this particular sequence, but this limit actually encodes the halting problem in the sense we've just discussed in our count example. So let's have a closer look at this Specker sequence. So the sequence index here is J, okay? And J governs how many terms at most we consider here. Namely, we consider only terms M ranging from 0, right? Computer science, natural numbers start with 0, up to, but not including J for simplicity. And the second condition is that this quantity T of M must also be strictly less than J, and we'll discuss this quantity in a minute. And then we add up all these binary coefficients that satisfy that, that condition. So let me say it again. Imagine this to be the binary expansion of the halting problem, okay? And we consider the first J binary digits, that's what this condition means, only M ranging from 0 to J minus 1, that's M terms, the first N binary digits of the halting problem. And that's because we only consider or we define the binary coefficient corresponding to M to be 0 or 1, depending on whether this condition holds or not, right? So if this condition holds, then the coefficient is 1, this term is present. If this condition is violated, then the coefficient is 0. And what condition is this here? This is the function that takes the code of a while program and argument to the while program, so just like in the halting problem, and counts how many steps this while program makes on this argument x, right? So in particular, if the while program terminates on argument x, if this is a positive instance of the halting problem, then t of that is a finite number, some finite integer, some finite natural number. Whereas if this never terminates, then the value of this function, we deliberately call this value infinity. So we include infinity to this extended set of natural numbers and thus make this a totally defined function. And of course, the value of that function can only be calculated in case that it is finite by using our simulator, by using our interpreter, simulating the given while program on the given argument x until it terminates, and then count the number of steps made until it terminates. That's the value. But if this value is infinite, that cannot be computed. That's just a mathematical definition. It is mathematically well defined, but it cannot be computed by any while program or any other computer. So the baseline is when this is finite, in particular the case when it is less than j, that is actually computable. And therefore every single entry of this sequence is a computable dyadic rational, namely with 1 divided by 2 to the m or 0 divided by 2 to the m, depending on whether this condition is satisfied for the first j entries. So this is a computable sequence, but what is the limit? Well, at first it's a non-decreasing sequence, right? So if we increase j, then possibly only further terms get added to this finite sum, but never removed. So this is a non-decreasing sequence. Possibly it could be stagnating for some j, or maybe for several values of j, but it will never decrease. So it's indeed a non-decreasing sequence, and it is bounded because, it's bounded by the whole geometric series where all these conditions are present, where all these terms are present, in which case it evaluates to 2, right? So 2 to the minus 0 plus 2 to the minus 1, and so on. That's an upper bound to the series. So it's a non-decreasing bounded series of real numbers, and therefore it has a supremum which coincides with its limit. So this number is well defined. But what is its binary expansion? Well, it has binary coefficient 1 at position m. This term is present if and only if this position m corresponds to, well, to a terminating Turing machine. This means that the number of steps made by this machine, by this while program and input, is finite, is less or equal to j for some j. When we take the limit of j to infinity, that basically means this is finite. And this being finite is just another way of saying that while program A on input x terminates, meaning that this is a part of this belongs to the, this is a positive instance to the halting problem. So that indeed all those binary, the digits in the binary expansion of this resulting real number has exactly 0 and 1, depending on whether the while program and input to the while program corresponding to that position m terminate or do not terminate. And this is exactly a binary encoding of the halting problem that I mentioned previously, which is therefore uncomputable and undecidable. Good, so now we've seen many examples. We've seen equivalence notions of computable real numbers. We've seen positive examples, and the first negative example as the limit as the supremum of Specker's computable sequence. But I keep referring to computable sequence without having defined it. I will define it on the next slide, but before that, let us also briefly, one slide, talk about oracle-computable real numbers and real counterpart to the arithmetic hierarchy that we discussed in the discrete setting. Okay, so what are oracle-computable reals? First, let us recall what it means to be a computable real. It means to output, according to one of the three equivalent definitions, dyadic approximations to that real number. And if we don't really want to know what real number, just ask how do dyadic approximations look like that are approximation to some real number, then the following condition is necessary and sufficient, namely that this ratio minus this ratio must be bounded by these two sums. So one direction is immediate. If the sequence an are numerators to dyadic rational approximation to some real number up to error 2 to the minus n, then by triangle inequality, the difference of these approximations do satisfy this condition, right? That's just triangle inequality. And conversely, if the sequence satisfies this condition, then we can proceed to the limit, right? Real numbers are complete. Proceed to the limit, replace that with the limit of that sequence, which exists because this is precisely the Cauchy condition, right? And the remaining approximation, an over 2 to the n, are up to error 2 to the minus n. Okay, so this is a reformulation of what kind of approximations are legal in a sense, and other kind of approximations do not refer to not approximations to any real numbers. That's the kind of message here. Okay, so and now let's recall from the discrete setting what is an oracle while program. So here's your ordinary while program, and an oracle while program can basically make subroutine calls to some external fixed function phi, which may or may not be computable. It could, for instance, be the characteristic function of the halting problem. And right, this is just some fixed arbitrary total function which need not be computable. And when it is the characteristic function of the halting problem, this gives rise to more powerful while programs, strictly more powerful. They can now, for instance, easily solve the halting problem by making such a function call. And there's this entire hierarchy. And similarly, we define what it means for a real number to be computable with oracle, with some arbitrary but fixed oracle, by saying that any of the three conditions apply, but now with oracle program, with while program replaced by oracle program. So put differently, the equivalence of these three conditions relativizes, as it's the common terminology in computability theory. So they're still equivalent when we add oracles, the same oracle to all three of them. Not different oracles, not distinct oracles, not just to one of them, but the same oracle to all three of them, which is easy to see. Now we can consider real numbers that are computable with, let's say, for instance, the halting problem as oracle. And as you recall, the Schoenfield limit lemma gave a characterization of which integer functions are computable with access to the halting problem as oracle. Namely, those were precisely the limits, the pointwise limits of integer functions that are computable without oracle. So you can replace pointwise limits, one can remove them when in turn granting oracle access to the halting problem. That was the message in the discrete setting. And in the real setting, of a similar statement, namely, if a computable sequence without oracle, if that converges, then its limit in general may not be computable. That's exactly what Specker's sequence here demonstrates, right? So this is a computable sequence in the sense that we will formalize in just a minute, but its limit, its supremum, is the binary expansion of the halting problem and therefore not computable. Well, unless we granted oracle access to the halting problem, then of course it becomes computable again. We're using oracle access to the halting problem. We can decide the binary expansion of the real number whose binary expansion encodes the holding problem trivially, right? And then a real version of Schoenfield's lemma. Lemma kind of generalizes that to other computable sequences. If this is a computable sequence, computable without oracle to the access to the holding problem, then its limit in general may not be computable, but it is computable when granting oracle access to the holding problem. So that's kind of the real version of one direction of the Schoenfield limit lemma, and the other direction, if you recall, says a counterpart, namely if a limit is computable with oracle access, then it is, now if a function is computable, integer function is computable with oracle access, then it is the pointwise limit of an integer function that is computable without oracle access. And here the real counterpart is the following. To every real number which is computable with oracle, there exists some computable sequence computable without oracle access, whose limit is that very real number. Or put differently, that's the important message that I'd like to repeat and stress here. Limits, classical limits, as you've been taught and learned in calculus, these are operations that potentially leave the realm of computability. Arithmetic operations, as we've seen, polynomials, all remain within the computable real numbers, do not leave. But when considering limit, then possibly that could leave the realm of computability, as does Specker's sequence, but they never leave it more than oracle access limits. When granting oracle access to the holding problem, then also limits are computable and not higher. So for instance, we never will need oracle access to the totality problem, for instance, to compute a limit. Okay, so that's a message, that's a statement of the real version of the Schoenfield's limit lemma. And now we should start proving it. And the proof is now very similar and easy, since we already know the statement and the proof of the discrete Schoenfield's limit lemma. And to prove one direction, let's suppose that we have a computable sequence, right? And we want to compute the limit, which we cannot in general, but we have now access to the halting oracle. So what does it mean to be a computable sequence? Well, I'll give the formal proof in just a minute, but it basically means that we can approximate every single element in that sequence. And so the approximation to the single elements also constitute approximations to the limit, right? Only we don't know how fast they converge to the limit. That's basically the question here. We don't have error bonds, we don't have rate of convergence. On the other hand, we know from calculus that there's a subsequence which converges as fast as required, namely with error rate 2 to the minus n, but we simply, calculus just says there exists a subsequence, right? But how can we compute that? Well, in general, we cannot. That's the whole point, right? We cannot, in general, proceed to a computable subsequence. If we could, then we could also calculate the limit without using oracle access. But the statement says, and the Specker's sequence demonstrates that in general, we cannot do without oracle access. And so let's use that by considering a subsequence, and the condition is written down here, right? So the subsequence must satisfy this condition, and this is a condition which must be satisfied for all pairs m and n, infinitely many. So we can never be sure whether we have kind of tried the right subsequence. So let's try the first, let's say, 5 element from the subsequence, the first 5 indices, and check whether they satisfy this condition. But this is a condition that involves infinitely many natural number arguments. But then again, we have oracle access to the holding problem, so we can convert the question whether this holds for all sufficiently large n and m into a while program that searches for counterexample for this to hold. And if this while program finds a counterexample, then it will terminate. And thus we have reformulate the question whether this holds for all sufficiently large n and m to the question whether a while program we have just artificially constructed does not terminate. And this is exactly what the oracle to the halting problem can tell us, and thus can tell us whether such a condition is satisfied for all sufficiently large n and m, and sufficiently large here gives rise to the first index of the subsequence which converges fast. And then once we've found that, then we look for the next index of the subsequence that again must satisfy this condition, and so on each time using the oracle access to the halting problem to determine the next sequence of the fast convergent subsequence. And when we have a fast convergent subsequence converging with error rate 2 to the minus n, that constitutes approximations to the real number with this error bound 2 to the minus n. So that's one direction of the proof of the real limit lemma. The first statement, if we have a computable sequence, then it's which converges, then its limit is computable with oracle access. And it remains now to prove the converse direction. If we have a real number which is computable with oracle, then there exists a computable sequence of real numbers computable without oracle access, whose limit is that real number. And this proof is basically the same proof as the also again as the Schoenfield's limit lemma. We replace the oracle with finite approximations, and then check, verify whether these approximations are actually approximations. I'm not going to repeat that part of the proof. Okay, so that concludes our first part of chapter 2, computable real numbers, with notions, properties, closure properties, examples, counterexamples, and these counterexamples we've seen so far reside on some level on the real version of the arithmetic hierarchy, namely they are computable with oracle access to the halting problem, but one can, and for instance Shizun Zheng and Robert Röttinger have created a real counterpart to the arithmetic hierarchy that you remember at the end of the lecture on discrete computability. So there exists an infinite hierarchy of real numbers that are more and more uncomputable, strictly more uncomputable. Okay, and this is almost the end of today's lecture. Of course, I will be happy and available to answer some questions, but as a perspective, as outlook, in the next part of chapter 2, we will talk about what it means to compute real sequences and properties of computable sequences. And let me just close with a repeatedly announced, promised formal definition of what it means to compute a real sequence. We've already used that, so you deserve to know the formal definition. Namely, it's basically a counterpart generalization of what it means to compute a single real number. To compute a single real number means to output numerators of dyadic rational approximations that approximate that up to error 2 to the minus n. And computing a sequence of real numbers means to similarly approximate every single entry up to error 2 to the minus n. So now here, the input is not just the desired error bound n for 2 to the minus n, but also j. So 2 natural numbers are input, and the goal is to approximate the jth element of that sequence with dyadic rational numbers. So that basically means computing a sequence of real numbers means computing a double sequence of integers, whereas computing a single real number means computing a single sequence of integers. And so Right, in discrete computability and complexity theory, we always consider like infinite problems, infinite subsets of natural numbers. Otherwise, everything is trivial. But these infinite subsets of natural numbers correspond in a real setting to a single real number, which is makes sense because a single real number is an infinite object in a certain sense. Only, yeah, for instance, binary expansion is infinite, but considering the binary expansion, that's only one of the three equivalent notions of computing a single real number. And similarly there, we can extend that to similar notions of what it means to compute a real sequence in binary and what it could mean for a real sequence to be approximated by rational fractions with arbitrary error bounds tending to 0. Okay, so that's all for today. Thanks for your attention.